Now would like to introduce our Design, Construction, and Logistics panel. Gentlemen, as you're introduced, please turn on your cameras and leave them on until all introductions are complete. Our first panelist is Archie Landerman, who is the North Central Regional Director for Woodworks, an initiative of the Wood Products Council. Archie has been with Woodworks since their Midwest inception in 2008 and has been actively involved in wood education and assisting with commercial wood projects. Some notable project assistance examples would be the T3 building in Minneapolis, Ascent in Milwaukee, and Buffalo Sabres Arena in Buffalo, New York. Archie has assisted on over 300 projects and provided hundreds of hours of education to architects, engineers, contractors, and developers. He has been active in the wood and structural building component industry since 1970 and has extensive experience with structural lumber, engineered wood products, SIPs, wood trusses, and mass timber. Archie works closely with the Forest Products Lab in Madison, Wisconsin, and is active in numerous professional organizations, including American Institute of Architects, Construction Specification Institute, Forest Products Society, and the National Frame Building Association, to name a few. Next, we have Kevin Marshall, who is a senior associate at Integrated Design Solutions. In addition to serving as project architect for the STEM teaching facility project at Michigan State University, Kevin has been involved with a significant number of complex university projects at both MSU and the University of Michigan, such as the U of M A. Alfred Taubman Wing and the MSU Eli and Edith Broad Art Museum. Kevin's professional interests revolve around building enclosure and codes, and he strives to create high-performing environments for his clients. Then we have Peter Heringa, a principal and vice president at SDI Structures. Peter is a graduate of the University of Michigan, where he received a bachelor's degree in civil engineering and a master's in structural engineering. He has over 10 years of experience designing higher education, healthcare, commercial, and athletic facilities throughout the United States and the Middle East. He enjoys working closely with team members to develop efficient and constructible designs while promoting the vision of the architect and owner. At SDI, Peter is responsible for engineering and analysis standards, maintaining the office commitment to code development, and emerging construction technologies. Next, Jean-Marc Dubois is the Director of Business Development for Nordic Structures, the building systems division of Canadian lumber manufacturer Chantier Chigugama. His career spans over 40 years in the building products industry with regional, national, and international corporations, focusing primarily on value-added and engineered wood products. Celebrating 20 years with Nordic this year, Jean-Marc's penchant for delivering customer solutions through value engineering and process optimization led him to join the Structures division, where he collaborates with clients, architects, engineers, designers, and builders to provide sustainable built mass timber solutions across North America. A passionate advocate for sustainability, Jean-Marc serves on several domestic timber research councils and has been a guest lecturer at universities, as well as architectural engineering and sustainability conferences across North America, Scandinavia, and Japan. And our final panelist, Bill Beaufaisal, serves as project manager for Grainger Construction and has more than 12 years of construction management experience. A strong leader, Bill promotes a lean culture and challenges his team to continuously improve through the adoption of lean construction practices. He enjoys building strong relationships with owners, architects, and engineers, and ensuring successful construction experiences. At Grainger, Bill is responsible for total project management, negotiating subcontracts, and providing day-to-day communication with the project team to ensure jobs remain on schedule and within budget. Bill earned a Bachelor of Science degree in Construction Management from Ferris State University. His experience overseeing all phases of construction projects spans several market segments, including higher education, healthcare, corrections, and industrial. Thanks, everyone. And this is a great panel that I'm sure the audience will see how well they have worked together on this awesome project. We have one break scheduled within this panel discussion, and we will have questions and answers at the end. We ask that participants in the audience please submit your questions in the chat box as they come to you during presentations, and they will be compiled and asked during the scheduled Q&A. Thank you, Archie. The virtual platform is yours.
Thank you, Donna. Good morning, Michigan, I would say. I'm coming to you just across the lake here in Wisconsin. And I hope it's nice over there because it's I'm an hour behind, but it's getting bright and sunny here finally. So this has been quite the project for everyone to put together. I know there's a lot of hard work that's gone into this. And my part, I guess you would say, is to really talk more in general terms about mass timber and kind of the state of what's going on currently with mass timber. So with that, if we could go to the next slide, please. So briefly, I want to let you know what WoodWorks does. I think it's vitally important that anytime anyone is speaking to you, you really have a good understanding of why and where they're coming from. So WoodWorks is a nonprofit organization. You can see from the slide what we do. We do project support, education, presentations like this, but primarily we like to get to the point where we can help work on specific projects, whether it be engineering, architecture, construction. That's really what we do. To that end, I simply say anything we can help you with, contact me anytime by phone or email. We're here to help. Next. So we're looking at mass timber, and we can see from this slide, an example of what we traditionally call heavy timber. It just so happens I am in a building like that here in Racine. I'm in a building that is about 600,000 square feet. The first part of this complex was started in 1857, and it's heavy timber like you see on the left, 4 stories. The point of that is what we're talking about today is not new, but there are new aspects to it and new products, new methodologies and things like that. But we're not reinventing the wheel. We've been doing this very capably for a very long time. So as we look to the right, that slide looks substantially different. That's the Bullitt Center in Seattle, which was completed in about 2013. And you can see that there we have glue-lam columns and glue-lam beams and nail-laminated timber floors. The slide on the left, of course, is more purely heavy timber. Next slide. So what is mass timber? Well, I'll let you read the slide. I don't need to read words to you, but this gives you a really good idea. So mass timber is really a new phrase. I was fortunate back in, it was about 2009, maybe 2010, the first CLT symposium or conference was held in Toronto. And I was, chosen by WoodWorks to attend that. And it was really, really interesting because there wasn't much going on over here in North America yet. Almost everything was European. And it was a 2-day conference. And that's where kind of the term mass timber, that's the first time I heard that. So that encapsulates all of these products, including the old heavy timber. But today we're using primarily engineered wood products. So in this slide, you can see that we're looking at cross-laminated timber, nail-laminated timber, dowel-laminated timber, or glue-laminated timber for these different products. Of course, columns and beams would be glue-lam or heavy timber. Next slide, please. So we can see some better examples or better photos of exactly what we're looking at here. So on the left, glue-laminated timber. Now, I'd probably be better if that was laying flat in plank orientation, because that's what glue-laminated timber really means. We're looking at a glue-lam beam, but you take and you lay that down in plank orientation, and you can use it as a floor. But one of the keys to note with that is that has to be specifically engineered to use if you're going to lay it flat. You can't necessarily just take an off-the-shelf glue-lam beam and do that. So engineering has to be checked to make sure that we can do that. It's done very commonly. We've just recently done a couple of projects here in Wisconsin using those type of products, and they work very well. Cross-laminated timber, I guess that's the one that gets the most press. That's the elephant in the room, so to speak. So the one in the middle is cross-laminated timber using solid sawn lams. So you could use a 2x4, 2x6. You probably could use a wider material. I think most of the CLT is manufactured with 2x6s. And as it says, it's cross-laminated. So the first layer would lay in one direction. The next layer would lay perpendicular after glue is applied, and so on to form a thick panel. And then over on the right, we have a structural composite lamination, or in this case, it's plywood. So Frere's Lumber happens to, they're the only ones that are currently doing this, called a mass plywood panel, which is comprised of thicknesses of 1-inch thick plywood. And then down below, you can get a little better sense of how some of these products are used. Next. We have dowel laminated timber, or DLT. There's only one manufacturer in North America at this time, StructureCraft, as you can see from the photo. Now, StructureCraft actually did the nail laminated timber for the T3 building, and the T3 building is the middle slide down below. That's nail laminated timber. But then they decided to start an operation and go into dowel laminated timber. So it's softwood lumber fastened together with hardwood dowels. That's very similar to the middle slide, which is nail laminated timber, or NLT. Now, nail laminated timber has been around, again, at least for 100 years. It has been in the codes, to the best of my knowledge, at least since 1967. So an engineer can use the National Design Specification and design a nail laminated timber panel. The dowel laminated timber, however, that is a proprietary technology. So that needs to be looked at specifically on that particular job and that particular use, and from a code standpoint and from a usage standpoint. And then over on the right, we have decking. So we have solid sawn decking, and we have laminated decking, which typically you can get up to about 5 inches thick. That's been around for a long, long time. And a lot of information can be found on the decking in the National Design Specification. AWC has some great information on that. So looking down below, we can see an example of you can see the gap between the panels that are laid there of the dowel laminated timber. Middle slide, like I mentioned, is Minneapolis T3. Over on the right, I actually don't know which project that is. I believe it's out on the West Coast. You can see the steel braced frames. Next. So post, beam, and plate. This again is a picture of T3, so we can see that we use glue-lam columns, glue-lam beams, and the nail laminated timber is made up of 2x8s that were nailed together into solid planks. So that's a post, beam, and plate type construction. Next. This is just a post and plate. So this is a photo of Brock Commons. Brock Commons is a 17-story university building at the University of British Columbia in Vancouver. It's done about 3 or 4 years ago. And you can see the absence of the beams here because they used the cross-laminated timber, which has bidirectional strength, and they're able to eliminate the beams in this particular use. This was a dormitory, so they didn't need wide open spans. So this lent itself very well to that application. Next. This is what we call honeycomb, or this is all CLT. So if you look at this, you can see down below, those are all CLT walls that were erected. They're currently setting a CLT floor panel. And I think what's notable is you can see how they assembled the fall protection prior to raising the panel in place. And again, this was for speed of construction. So once they dropped those panels in, workers could actually work above and they could work below because everybody was protected. This particular job is the Redstone Arsenal that was done in Alabama about 4 or 5 years ago now. Next. Then we have light frame. We can take light frame construction and use any type of plank type material, whether it be CLT or nail laminated timber. I think the key to this type of construction, any of the types that we're looking at, is saying what is the best product to use where? You know, is light frame wood, does that make more sense instead of post and beam? Something that we have to look at very early on. But these materials can be used very well together. They complement each other. Next. Here we're using steel and wood. And I like to tell everybody that steel and wood and concrete and wood play very well together. You know, we are wood guys. We like to see wood used, of course, but every material has its right application. And in some cases, it just makes more sense to do maybe a steel frame and use the wood decking. Next. So Brock Commons, this is what I mentioned before. This is a precedent project that was done. So we're just going to look at a few different projects here to give you a sense for what's been done. This was in Vancouver. Next. Dalston Works, I don't know too much about this. The architect, Waugh Thistleton, back in 2008, did the first CLT building in London. It was an 8-story over 1-story of concrete apartment building, small footprint, all CLT. And they've since done quite a few CLT projects. This, to the best of my knowledge, is the largest CLT project currently being done in London as we speak, and they have done hundreds of CLT and mass timber projects in London. Next. This will give you a better sense for how much mass timber is currently being done. So this is based on June of this year, and we can see that we have more than 380 built and more than 530 in design. It's interesting to note there's a lot on the West Coast, but there's also a lot on the East Coast. And there's probably more actual buildings being done on the East Coast currently than on the West Coast, even though West Coast had a jump. And of course, you know, everything's finally filtering into the Midwest here. Next. Other precedent projects, Carbon 12. This was an 8-story building that was done about 7, 8 years ago in Portland. This was really the first tall wood building. It's still currently the tallest that I know of in the U.S. Next. T3 Minneapolis, we mentioned 6-story wood office building over 1 story of concrete. There's another one that's under construction. Has got to be pretty close to being finished in Atlanta, and there's other ones on the books that will be happening. Next. 111 East Grand in Des Moines, and all of these projects, by the way, Woodworks has been involved with in one way, shape, or form. I worked with the architect and Ryan companies on this particular project, and they actually occupy this office building now. Now, next, we'll see one more slide of East Grand. So that was the dowel laminated timber panels. Next. Bullitt Center was done in about 2013. We saw a previous slide of this Living Building Challenge certified building. 2x6 nail laminated timber deck, 2x4 roof deck. Next. And even in Brooklyn, New York. So this is being done everywhere. And New York, I believe, will be a hot spot from what I understand. Our engineer out there that works on a lot of these projects is they're kind of getting a foothold and things are happening. There's a couple other projects I'll mention that I don't actually have photos for. One is the Ascent building in Milwaukee, which is a 25-story mass timber building that has started construction. It started groundwork. It's right in downtown Milwaukee. That currently will be the tallest mass timber building in the world. So that's really a high-profile building. It's been very cool to be involved with that. Another one that's under construction is the Intro job, which is a 9-story building in Cleveland, and that is also under construction right now. So there's things happening in the Midwest here too. Next. So I mentioned that this construction isn't new. This is a photo of the Butler Square building in Minneapolis. It's a 9-story wood building that was built in 1906. It was, let's say, rejuvenated in the early 70s. They opened up the interior into this atrium. You can kind of see that here with all these offices and studios and things. And they used to have a restaurant in there. I know it closed. I don't know if they're replacing that. Very impressive building, 500,000 square feet. Obviously, it's performed very well. Next. So we just want to say, moving on, 2021 IBC, we do have 3 new construction types that are going to allow us to go taller than what current code does. So 5A, 18 stories, I'm sorry, 4A, 18 stories, 4B, 12, and then 4C, 9 stories. We do have a lot of information on this available. Next slide. So this just gives you a little pictorial of what those building types are like and what will be happening. Now, Washington and Oregon has adopted this code. Denver has adopted this code. I'm working with other people that are using provisions from this code to do buildings. So it's well on its way, and we should have it should be in hard copy here anytime soon. Next. We do have some information on our website regarding the 2021 IBC. That's available. I would just suggest that anybody who's interested in wood construction, look at our website, woodworks.org. There is just a ton of information available there to you. The other one I would mention, a partner organization of ours, is the American Wood Council, or awc.org. And another website of note would be thinkwood.com. Just a lot of information to be had there. Next. So that brings us to the end. My contact information is here, as you can see. Feel free to call. Let us know what we can do with anything to help out. And I really appreciate your time, and I will switch this over to Kevin. Thank you.
Thanks, Archie. We get to kind of come down a little bit from Archie's super high view of mass timber to a little bit more granular as to the design process at Michigan State University, and you start off with why timber. We've talked about this in other sessions. We just wanted to bring it, reiterate a little bit of what that was, some of the reasoning why we chose to go with the mass timber route. But it wasn't done in a vacuum just with the thought of mass timber alone without looking at it, some other metrics to it. Next slide, please. So this is a slide that we produced for the executive steering committee in the project that kind of was using like almost a choosing by advantage matrix for steel versus mass timber and which had the advantage to kind of to see what was the right solution for MSU, for the STEM building, and for the project overall. So we went through this process in order to solidify and justify the use of a new technology for Michigan State University. Next slide, please. So next, when you start moving into something new, is how does the code authority see it? With the STEM building, the primary code authority is the State of Michigan's Bureau of Fire Services, which works under NFPA 101, the 2012 edition. And so we joined with them early on in the process, even before we made a full commitment to going to mass timber, to start bringing them up and helping us with some decisions on what type of construction is this? Is this type 3 construction or type 4 construction? And what are the pluses and minuses of each? Type 4 construction, which is the traditional heavy timber type of construction, seems like the obvious choice, except when you start reading into the fine print, where it limits you on concealed spaces and things that are going on within the building. And because we had certain spaces where we wanted to put ceilings, and we had our shafts, we wanted to be able to enclose our shafts for the chemistry and the fume hoods and those kinds of things. The State of Michigan Bureau of Fire Services determined that this was probably more of a type 3 building. And 3B, in fact, because our size of our footprint met within the area requirements for the code. And then that also allowed us to go with steel up on the penthouse, and we could use a hybrid construction method. And then the last part that they were really concerned about was we were using CLT as part of the fire rating, or to get the fire rating at our egress stairs. And so we held a meeting with diagrams and sketches and drawings and discussed the pros and cons of different detailing methods in order to establish how the fire rating would be handled, whether it would be done with the wood itself, would it be done with a more traditional gypsum shaft wall construction or something like that. And we ended up going to the 7-ply CLT wall panels that you see in the building today. Next. So now what? We've made a commitment, we've got some information from the code official, and we look at what are we doing? We doing wood or steel primary structure? Well, in the case of the STEM project, it became a both. On South STEM in particular, due to the heavy mechanical loads for the chemistry and biology labs in the building, the size of the air handling equipment up in the penthouse got quite large. And that induced strong loads coming down, vertical loads through the building. And we determined that we would use steel for those columns in those places, kind of surgically placed within the building, to keep the size of the column from taking too much space out of the usable area within the building. Next slide. And a structural wood floor deck. We had different options on that. In the upper right-hand corner picture, you'll see a photo from University of Massachusetts at Amherst, where they used a composite deck with the wood and the concrete working together to get the spans that was needed for that project. We chose a little simpler solution where we let the wood do the work, and the concrete topping, as you see, was getting prepared for in the lower slide or image, was just a topping, a wear topping to protect the wood and give the working surface of the floor. But that meant that we had to introduce more wood members for the beams, but it solved some inherent problems that they had at University of Massachusetts with their composite floor slab. Next. And what kind of floor? Archie was talking about, well, how do you do this? Do you do it with CLT, NLT, DLT? What is the floor structure going to be? And this became a little bit a function of our discussion with our mass timber provider as to what they're traditionally work with and how they work. We had some thoughts of going with nail laminated timber to help with some acoustics. to be able to stagger the bottoms of the beams in height in order to break up the sound in the labs. That became less and less of an issue as we worked through the design, and so we decided to go with the more panelized construction and take care of those efficiencies, and ended up with CLT floor decks of a 4-ply situation, which is a little different than usual. And it was 4-ply due to vibration concerns for the long spans in these open labs. Next slide. And what about walls and shafts? We talked a little bit about how the code authority sees it. You saw it briefly in the upper right-hand slide, a photo of the 7-ply stairs at the MSU STEM project. And then at the bottom, you see one of the stairs completed, and the stairs are hung off of the wood. The wood is doing work, and it also carrying its rating. But we chose not to use the shafts, and we could have done shafts with CLT as well, but we chose not to for future access to get into and make changes to the building as it's used. I mean, this is a 100-year building for the university. We wanted to keep it a way that they could operate in the building and make it continually work for them. Next slide. Combustibles in the exterior wall. I think Pete will talk about this from SCI a little bit in his talk, but one of the things with type 3 construction is if you have an exterior load-bearing wall, it needs to be non-combustible. And anytime it gets over, I think, 100 pounds a linear foot of support, it's considered a load-bearing wall. Well, with our facade, we had more than that weight, and we couldn't introduce the wood timber into the exterior wall, or otherwise we would have had to rate all of the wood timber to create that 2-hour fire rating of a load-bearing exterior wall. So as the walls are non-load-bearing per the definition in the building code, we were able to keep the structure lighter as we did, but we had to introduce this exoskeleton of steel to help support the brick and the precast and the glass that will be going on the building here in the near future, or actually is in the South STEM building right now. Next. And having mechanical loads. How do you handle the weight and the difference? And we wanted to keep repetition in the bays in the lab so they looked similar and were uniform. And when you start getting the mechanical equipment up in the penthouse, it has very specific requirements for support, and that we chose to do that out of steel to help with the steel member side, with the member sizes and the bay spacing, and also as an isolation from the penthouse to the 3rd floor, and did that with the steel structure hovering just above the columns and the wood deck that is the roof deck of the 3rd floor. So we chose to use a hybrid based on where, as Archie says, where wood it makes sense and where steel made sense in order for the building to perform as well as possible. And I think that's about the end of my talk, so I'll turn it over to Pete.
Thank you, Kevin. I'll start my portion out with a bit of a detour. I came across this quote. A crude analysis is that Thoreau, the American philosopher, along with his contemporaries, believed that knowledge or truth could be found simply by spending time in nature. And in Thoreau's case, in the 19th century, this literally meant in the forest amongst the trees. So I think it's fair to say that 200 years later, that the MSU STEM project would have interested Thoreau, and he may well have been a supporter of mass timber construction. Next slide, please. I'd like to focus my time this morning on the unique considerations for the structural engineer when designing mass timber. And I'll start with member materials and member sizes. So initially, when we began the design process, as Kevin said, once mass timber has been selected for your project, one of the first questions we ask ourselves before we can size members and evaluate is, what are the proper material properties? So we did a lot of investigation into what is available, what kind of material strengths can we achieve from the primary suppliers. Those are some of the early questions that we worked with Woodworks on. And then the slide in the picture in the upper right-hand corner is just a snippet from our drawings conveying the expected minimum properties for the timber suppliers to bid off of. And this was representative of something that is widely available, that is going to give us the most efficiency in terms of member size without being too restrictive of the materials. Another important consideration for members is the typical sizes. So we did a lot of research into the commonly used dimensions of both beams and columns. They're not consistent. So you typically don't get beam member sizes in modules like you do columns. And as much research as we did, it still, in the end, wasn't the sizes that Nordic preferred to use. So that's something that's important to keep in mind, is that despite doing a lot of research and asking questions to different suppliers to maintain consistency through design and construction of those member sizes, inevitably the supplier may have their preferences based on how they fabricate their fabrication setup. Next slide, please. Other next unique set of considerations, the gravity system. So as Archie talked about, Kevin talked about, what is the choice for decking? Is it NLT? Is it CLT? Is it GLT? CLT has some unique advantages, one of them being dimensional stability. The layups in the CLT are positioned in such a way that the CLT panels themselves are dimensionally stable. So there's very little concern with CLT in terms of shrinkage or movement during construction or during the occupied building. And so considerations like joint spacing, joint location, size of joint to deal with issues of shrinkage are just less of a consideration or concern with CLT. How thick is the panel? What is the span? Architecturally, what is the desired spacing of the beams? What is the bay size? At MSU STEM, the real driving factor in a lot of the design was the minimum bay size for the classroom spaces. So dealing with a 40 by 40 open space that needed to be column free. And so that drove a lot of considerations in terms of the panel thicknesses, the beam depths, and the beam spacings. Another important consideration is floor penetrations. What kind of floor penetrations are you looking at? Is it residential, where you're looking at things like showers, toilet drains, those kinds of things? Or is it a student academic laboratory facility like MSU STEM, where there are lots of floor penetrations for lab equipment, sinks, that don't necessarily stack from floor to floor, but there may also be a lot of dedicated shafts, which we also had at MSU STEM. So in our choice of CLT thickness, in addition to consideration of floor vibration and shrinkage and strength, we really wanted to make sure that there was enough reserve capacity in the CLT decking such that every time there needed to be a small floor penetration for a drain or a conduit, that we weren't looking at having to introduce some sort of supplementary framing. So that's a consideration that we would recommend focusing on early on in the project, so that later on, when we know issues are going to come, from a seismic standpoint, are you looking at steel brace frames, concrete shear walls, CLT shear walls, wood brace frames? Depending on the system choose, there may be an R factor directly in the code, or there might be another path towards approval that's necessary. From the diaphragm, are you looking at a composite system where the CLT and the concrete are working together? In the case of CLT, the picture on the upper right-hand corner shows the spline that connects the plywood spline that connects two CLT panels. From a design standpoint, the strength of the diaphragm is consistent or the same as would be for a normal plywood diaphragm. It's governed by the capacity of those splines. However, it's much more than just a plywood diaphragm. It's got considerable thickness. And so on MSU STEM, our design considered both a flexible diaphragm approach as well as a rigid to make sure that we captured the possible behavior of both types of stiffnesses. Another important consideration is load path. Unlike concrete and steel, these components and the way in which forces are developed through them really relies on a lot. Nothing can be taken for granted. The fasteners that connect these components are dowels and screws and bolts that really require the engineer to think about how forces are moving between lateral system components. Next slide, please. Another important consideration are your connections. And so first off, connection style. Unlike steel framing or concrete framing or conventional wood framing, most or many of the connections in mass timber are exposed. And so it's important to have a conversation with your designer and the owner early on to establish an understanding about what the connections are going to look like. There's also a difference in how forces are developed through connections. Unlike conventional concrete or unlike steel to steel, mass timber is very frequently developing forces through bearing and through shear and screws. And so that also introduces unique considerations in how members and components are designed. Issues like eccentricity become a consideration. We work with Nordic's connection engineers to really develop an understanding between ourselves and them on how the forces are being transferred from the floor beams into the girders in such a way that the girders are not twisted, that the forces develop concentrically into those girders. And also longevity and durability are also considerations. If the connection is exposed and it's low to the ground, is it going to be exposed to water as people enter the building? Is it going to be exposed to chemical cleaning agents during the life of the building? So those are also considerations. Next slide, please. As Kevin mentioned, with a type 3 building, the fact that you're not allowed to use combustible materials in type 3 construction in a academic facility that has a higher design use of masonry, heavier masonry cladding elements, anchorage and support of the facade is really a unique approach in mass timber versus, say, a conventional, again, concrete or composite steel construction. The photo in the upper right shows a portion of the CLT decking at the roof where there's a couple of shaft openings. So in this instance, there's shafts or rooftop openings that are located at the roof level. There's anchorage of the facade that's necessary, but there's also consideration of the panel joint locations near the edge. So that heavy black line that's running kind of up and down the photo, that's a panel joint in the CLT. The gray rectangles along the edge are actually connection points of the facade. And so to anchor the facade, the load really needs to move around the shafts and between panels. And so that's really a unique consideration depending on the side of the building, whether the panel joints are parallel or perpendicular to the edge, but also is there a slab step? Is there an opening in that diaphragm where the load really needs to move around? So consideration of panel orientation, joint location. Is there a joint 2 feet from the edge of the slab or the deck, or is it 8 feet away? Is there a slab step? Those are important considerations in design as well. Next slide, please. Another important topic that's unique is the amount or the extent of delegated engineering. I think a good way to think about it is that the responsibility for the member sizes, the design of the members, the column sizes, the beam sizes, the brace sizes, the CLT thickness, those that responsibility really is best placed with the engineer of record, the design engineer. How those components connect together, that's frequently a good choice or an opportunity to provide flexibility for the fabricator. Rather than detailing out all of those connections, providing for fabricator preference, erection preference, connection, and fastener preference is really an important consideration. So in the case of MSU STEM, we provided Nordic with beam shears, column uplift forces for splicing, brace forces, connection forces, so that they could take those components and tie those components together to complete the load path. That was not something that we felt was best suited to be fully detailed on the documents, communicating more of the intent and then the forces to complete that load path. Other kinds of forces that are important on the documents are forces for bracing those exterior walls, diaphragm shear demands. These are all things that fabricator preferences can introduce efficiency in the overall product. Next slide, please. A couple other important themes. Again, back to connection style. You're looking at in a mass timber structure more exposed connections. So are the owner and the architect looking for something more modern and sleek, or are they looking for more of the heavy industrial look? Archie shared slides really that kind of span that spectrum of different types of style and aesthetic. Other considerations are fabricator preference. Does the fabricator or the erector, do they prefer dowel type fasteners, bolts, screws, nails? There's a variety of options, but the fabricator's preference may, on a project the size of MSU STEM, fabricator preference and constructability preferences really might be the most important consideration. So kind of balancing connection style, fabricator preference, load demand are important in mass timber. One other consideration is durability. Is it something that could easily be damaged over the life of the structure, deteriorated? Could the look of the connection or the column base be affected over time? Those are important considerations as well. Next slide, please. So in summary, as a structural engineer approaching a mass timber building, I think it's important to pay careful attention to the load path of your forces moving through the building and the connection components. Pay special care in the detailing, visibility, durability, fabricator preference. And one other item that I didn't touch on, but we will touch on more, I think, with Bill and John Mark is trade coordination. The photo that we're looking at on the screen really shows the complexity of trade coordination. We're looking at a steel skeleton for support of the heavy masonry facade. We're looking at steel introduced on the edge of slab for support of that facade. We're also looking at the mass timber columns themselves, but those have steel bases below. So one of the things that our team did for the mass timber or the MSU STEM project is to try and provide clarity to the CM and to the bidding contractors on where responsibility fell. So on our documents, we actually used colors to communicate scope responsibility, where, for example, items, connection components and steel components that were shown with the color blue represented scope that fell with the mass timber supplier, where steel components that were shown in black on the documents fell with a steel subcontractor. And where sometimes those components ended up in the same detail, and coordination between those trades ended up being necessary. So there is, when you have a mix of steel and mass timber in your building, it does introduce trade complexity. And maybe Bill and Mark can speak to that, but it's as much as can be clarified in the bidding documents. I think that sends things down a better path. So I believe that's my last slide, and I think we may pause for some questions here.
Yes, thank you, Peter. If I could get Archie and Kevin to bring their cameras up as well as yourself, so we can field some questions from the audience now as we have a few minutes. Thanks. Okay, first question is for Archie. What is the breadth of project types that can use mass timber, just limited to office and multifamily residential type buildings? Any commercial, industrial, or transportation types of applications?
Now I'm not muted anymore. I had to take care of that. Yeah, that's a great question, because interestingly enough, we're actually doing a presentation tomorrow. One of our engineers has gone through and looked up doing tilt up with mass timber. So I guess the simple answer is it's really up to your imagination what you can do, but it's obviously restricted by practicality and economics. So mass timber has the potential to be used in all types of buildings, depending on certain limitations and things like that. But I think the trick is to say, what really makes sense. So it just needs to be looked at that way.
Okay, thanks. Kevin, this is for you. Could you tell us a bit more about the decision matrix for the choice between timber versus steel frame for the MSU building?
Oh boy, this is going in the Wayback Machine, because that was quite a while ago that we did that. If I remember correctly, we looked at what was the the safe solution of steel or concrete, what was the stretch of wood, and what the advantages were and disadvantages. I don't off the top of my head, I can't remember what that slide read, and I don't want to misquote things. But given using them and trying to use objectively with giving them points based on categories to see how they would fare on a level playing field. So you try to take emotion out of the decision process. And we think we did that pretty well with our advantages and disadvantages of each material, to come to our solution. But that it does still end up in the end with being kind of a gut check sort of a thing.
Kevin, would you say too an important ingredient in that decision matrix is owner interest and curiosity in the timber?
Yeah. Certainly, that's one of the weighing factors that you give these different answers, different things, weight and points, and see what scores the highest sort of a solution.
Excellent, thank you. This is for any of the panelists. What's the best way to mitigate the learning curve with mass timber projects? In hindsight, what would you suggest is the best way to approach a project when considering a mass timber design?
I think attending this seminar is a good place to start. That's the goal here, is to help. I think at least structurally, that was part of my goal, is to help folks jumpstart their next project. Personally, I'll say from the structural side, really questioning everything, questioning whereas in a lot of other structural systems, I'll say reinforced concrete is on one side of the spectrum, in terms of components come together very robustly. The load path provides for a lot of continuity through reinforcement. So I think our office approached things in terms of questioning everything down to the materials, how each individual component comes together, what kinds of things are we not thinking of. So there's a lot of resources that are available through Woodworks, in terms of, examples are the CLT manual is an excellent reference. Suppliers like Nordic and Structurlam have resources that are available. Nordic has a software that they publish themselves that is a sort of a offshoot of the NDS software that's available, but it offers design checks using the Nordic products, and that was something that our office used once Nordic was on board. Structure Lam has some design guides that they've published on CLT diaphragm and connection design. So I think initially we started by collecting every single mass timber resource that was available on the internet. When we were looking at vibration of mass timber for long spans, we found PhD theses from students in Europe, and we were looking at those to find any available resource, really turning over every rock to make sure that our design approach was consistent with the best available information. So a lot of gathering of any resources that are available is an important first step.
And I think also, the sooner you can bring on your mass timber provider and supplier, not to steal anybody else's thunder coming up with any additional presentation coming up, but that aids in directing you down and right sizing and value engineering and all the buzzwords for creating the most efficient building you can. The sooner you can bring those people on, then I think the better the project would be.
Great. I'm sure we'll be continuing to emphasize that throughout the presentations. Archie, they noticed that the stick wood frame construction can be used with mass timber in one of your slides. Is that more costly than the steel stud framing used in the MSU building?
Well, I can't speak to that because I didn't have a comparison for cost. There's other reasons why. I think it could be substituted pretty easily. I think the cost would probably be similar, but that's opinion, not fact. But there's other reasons why someone might say, well, we'd like to use light gauge steel in place of wood in this application, whether it be could be a fire, not necessarily fire resistance, but it could be a UL assembly. It could be just the fact that the contractor is proficient at light gauge steel framing and they prefer to do that. So I think the two are, for the most part, interchangeable depending on certain factors.
Okay, thank you very much. Virtual round of applause for all of you, and we're going to move now to our break. And we will come back at 9:40 a.m. to continue with the rest of this panel discussion. Thank you, everybody.